vibrant research can be done.
Research can be done. Okay, okay, okay.
Yes, sir. Thank you, sir. Thank you.
Thank you, thank you, thank
Nice
you.
presentation.
Thank you so much, Professor V. Parmeshwaram, for your excellent inputs on the topic emerging areas in statistics. Like it was really an enlightening session for us. Now we will move on to one more important session. So I request Sridevi ma'am to introduce the renowned Professor Srinivas Rao Jammalamadaka.
Thank you, Susrita. Honorable Principal Sir M. Sarath Babu Garu, Chief Guest of Honor, Professor V. Parameshwaran and Professor Srinivasa Rao Jammalamadaka, my dear colleagues, friends, academicians, and research scholars. Today I am here before you in this international webinar due to the blessings of my gurus, Professor K. Nirupama Devi, Department of Statistics, Andhra University, Professor K. Srinivasa Rao, Department of Statistics, Andhra University, and Professor late J. Lakshmi Narayana. It's my privilege to introduce Srinivasa Rao Jammalamadaka, formerly J.S. Rao. Sir did his B.Stat in 1964, M.Stat in 1965, and PhD in 1969, respectively, from ISI Kolkata. He was a visiting assistant professor and assistant professor, Indiana University, 1969 to 1976. Assistant and associate professor, University of California at Santa Barbara, 1976 to 1983. Professor, University of California at Santa Barbara, 1983 onwards. Distinguished Professor, University of California, Santa Barbara, 2003 onwards. Distinguished Visiting Professor, Geetham University, Vishakhapatnam. Academic Honors. Elected a member, International Statistical Institute, 1977. Elected Fellow, Institute of Mathematical Sciences, 1990. Elected Fellow, Institute of Combinatorics and Applications, 1990. Elected Fellow, American Statistical Association, 1993. C.Y.O. Connor Fellow, Curtin University, Division of Engineering and Science, Perth, Australia, 1994. Honorary Doctorate, Swedish University of Agricultural Sciences, 2012. Elected Fellow, Indian Society for Probability and Statistics, 2014. Sir is an editorial member for Statistics and Probability Letters, Journal of the Indian Society for Probability and Statistics, Journal of Non-Parametric Statistics, Stochastic Modeling and Applications. His publications are close to 200 articles and 3 books. Sir supervised 45 PhD students and received the Outstanding Graduate Mentor Award from University of California, 2017. The world-famous statistician is our distinguished visiting professor, Geetham Vishakhapatnam. I warmly welcome you, sir, to give your valuable invited talk. Thank you, sir.
Thank you, Sridevi. Thank you for that long and wonderful introduction. And I'm very happy to be here. And I did not know about the connection to Mahalanobis, to National Statistics Day, until recently. And then I think it's only appropriate that I say a bit about PC Mahalanobis, because among all of the people here in the audience, as well as you, I may be the only one who has had some personal interactions with PC Mahalanobis. And I will start by saying 1960, maybe none of you were born at that time. That was the year when the ISI, the Indian Statistical Institute, started the degree programs, the BStat and MStat. I was in the first batch of BStat, Bachelor's Degree in Statistics, a 4-year degree program. And in the first batch of MStat, BLS Prakash Rao was one of the students, and so was Subramanya Swamy. Any of you recognize this name? Our politician. Subramanya Swamy was a student at ISI Calcutta in the MStat first batch. Any case, that's a side story. Mahalanobis, coming back to Mahalanobis, Mahalanobis started teaching us mathematics the first quarter of our stay in ISI Calcutta, August to December of 1960. He picked this book written by G.H. Hardy called The Course of Pure Mathematics. It's a very famous book, A Course of Pure Mathematics by G.H. Hardy. Why did Mahalanobis pick up this Hardy's book to teach us from? Mahalanobis knew Hardy at Cambridge University. And so did Mahalanobis know Ramanujan, famous Indian mathematician Ramanujan. And in fact, I don't know if any of you have seen this movie called The Man Who Knew Infinity. Did any of you see this movie? It's a wonderful movie, The Man Who Knew Infinity. It's about Ramanujan's life story. And that movie shows two of my teachers there. One of them is Mahalanobis, briefly, of course, and then one of them is J.B.S. Haldane. He was another one of my teachers who taught me genetics and biology. Both of them show up in this movie. Anyway, that's okay. So Mahalanobis, I started, learning mathematics sort of in 1960 from him, and then we'll move forward a bit. 1965, I finished my degree program in 64, master's degree in 65. In 65, there was an external review committee, the budget review committee of the central government in India, who was looking at the ISI budgets and asking questions like, why does ISI have a biology unit, a geology unit? We have something called geological studies unit. And there were these very basic questions. The Statistical Institute, why the heck do we have all these other units? So Mahalanobis was hard put to answer these questions. So I happened to be instrumental in answering this puzzle for him. And in the sense that this person, geologist, was collecting data on directional data, something about paleocurrents. I talked about this at Geetham about however months back. And so then I got involved in this area of directional data, helped write some papers, and then Mahalanobis was apparently so pleased about this entire episode. This geologist wrote an article when Mahalanobis passed away and said Mahalanobis was so pleased. I'm trying to see what the Mahalanobis, this whole episode greatly pleased Mahalanobis. This episode of trying to connect geology with statistics. And so that is another way I got to know Mahalanobis. Mahalanobis was very pleased with this young statistician. That's me in those days, who helped this bridge the gap between geology and statistics. And then we'll fast forward again. In 1969, I finished my PhD and I was going for the what's called oral interview, viva voce as they call it. The external reviews were already in, they were outstanding, so it was a formality. So my interview took place in PC Mahalanobis' house, which is called Amrapali, inside the ISI campus. Amrapali means mango grove. And that is where my interview took place. There was no blackboard, there's no whiteboard. There were 3 members of my committee, which was P.C. Mahalanobis and R.R. Bahadur, and then C.R. Rao. C.R. Rao was my formal advisor, and so these were the 3 people. And given that the committee reports were all positive, the discussion was mostly about Brahmo Samaj and my job that was going to take up at Indiana University in 1969 and things like that. So Mahalanobis is someone that I knew sort of a bit, from the past. So I thought I'll mention a few anecdotes like this. Okay, then I'll start with my talk now, and I shall share my screen. Okay, you guys get to see my screen? Do you get to see my screen?
Yes, sir.
Okay, wonderful. Okay, I shall make this big and let's see, full screen mode. Okay, so my talk is called Gaps Between Observations. What can one learn from them? This is actually a mathematically oriented talk. I made it sort of common title here, but I'll get into mathematics pretty soon. So as someone mentioned, I have an affiliation with Githam University. Githam, you call yourself deemed university, but I call you a university. Anyways, yeah, so I have this title. And so what is that I'm going to tell you about? So it's about, I start already with a random sample of observations x1, x2, xn minus 1. Let this be a random sample from some continuous distribution, capital F, on the real line. So we have a real line like heights of individuals, weights of individuals. These are random observations on the real line. So these random values, I call them capital X1, capital X2, capital Xn minus 1. You will see why I picked n minus 1 in a minute. Usually people think of a sample of size n. In any case, I take n minus 1 for a reason that you will see in a minute. So simple spacings are what we call one-step spacings. Spacings is the word I use, are the gaps between successive ordered observations. So you order these observations on the real line and then look at the gaps between observations. What is the lowest value? What is the second lowest value? And so on. What is the gap between those 2 numbers? So those are called gaps between observations, and these are what I call spacings. Spacing is a common English word. So we're not using the original data x1, x2, xn minus 1, nor even the order statistics. Those of you who do statistics know order statistics are ordered values of x1, x2, xn. But I use only how large the gaps are between the observations. So not the data, not the ordered data, but just the gaps between data points. Okay, and I'm going to tell you how these gaps can be used to consider such spacings, get gaps, for testing the classical goodness of fit problem, or comparing 2 samples. How do you compare? If I give you sample of heights of a group of men and a group of women, how do you compare these 2 samples? So I'll tell you all these. Okay, scanning is not complete. It's okay, about to scan. No, okay. Oh, no shit. Okay. Okay, what's going on? Okay, now. So I'm going to tell you what is called statistical inference, testing of hypothesis. Testing what? Goodness of fit. How well does the data fit a given model F? How well does a data fit goodness of fit? I'll explain these things as I go. And this is my first slide, so I'm just explaining what I will be doing. Goodness of fit problems and comparing 2 different samples, heights of men versus heights of women. Are these 2 from the same distribution? Things of that nature. And then estimating unknown parameters. So that's another one of those common statistical inference issues. Estimation. Testing of hypothesis, estimation. These are two major topics in statistical inference, mathematical statistics. So I'm going to deal with those using only the gaps between observations. So the goodness of fit problem is one where one wants to test the hypothesis that the F, the true distribution, is a given distribution F naught for a specified CDF. CDF is the cumulative distribution function, F naught. So F naught is a given distribution, like for example, a normal distribution with mean 2 and variance 5. I'm asking, is the F, what is F? F is the distribution for the data points. X1, X2, Xn, I assume they come from F. I'm asking, is F a given F naught? That's called a goodness of fit. How well does the data fit this particular model F naught? And there are many approaches for doing this goodness of fit problem. And one of them is the chi-square method. So I'm not getting into great detail. I'm going to focus mostly on this gaps part. So, but I'll tell you, broadly speaking, for testing goodness of fit, there are chi-square based methods. And there are methods based on empirical distribution functions, and like the Kolmogorov-Smirnov statistic and so on. And then there are those based on spacings, which is what I'm going to talk about. There are many other ad hoc tests for specific contexts, like for example, testing exponentiality. You know, exponential distribution plays a prominent role in reliability. And so people have invented a number of tests for testing whether a given data set is from an exponential distribution. I myself have 3 or 4 papers on testing exponentiality by itself. But nevertheless, I'm saying broadly speaking, there are 3 approaches: chi-square based approaches, empirical distribution function based approaches, and those based on spacings, the ones on which I'll elaborate. So what is that I do first? To use spacings, we first make what's called a probability integral transformation. What is that about? You remember the F naught is a given distribution that I'm asked to test. So I apply F naught to all the data points x1, x2, xn minus 1. So yi is defined to be F naught of xi. Okay, so what is this? This is called a probability integral transformation. What it does is F naught is a function that takes you from the real line where the x's live to the interval 0 to 1. So yi's are on the interval 0 to 1. Not only that, if F naught is the true distribution, then yi's will follow a uniform distribution on 0, 1. So we'll skip the detail. So the yi's, the point of making this transformation is these yi's follow a uniform distribution on the interval 0, 1. And the question of testing whether xi's follow F naught translates to a question of whether yi's follow a uniform distribution on the interval 0, 1. What's a uniform distribution? It's a random points on the interval 0, 1. So that's much interesting question. The question is, on the interval 0, 1, I give you n minus 1 points and I ask you, are they randomly distributed, uniformly distributed? They can be any place with equal probability. That's what a uniform distribution is. And then what I do for this is, I find the order statistics. Order statistics are this, y naught, y1, y2, yn minus 1 are the ordered values of the transformed data on the interval 0, 1. And I define the y naught, there's no y naught in the original data. I call 0 the y naught, the lower end point of the interval 0, 1. And the upper end point, I will call it 1. Okay, so what's happening? I have n minus 1 points, and I'm taking the lower value on the interval 0 as one of the y naughts for mathematical notations that come later, and yn to be a 1. And that's 3 lines is a matter of definition. Okay, so now these simple one-step spacings are then the gaps between successive order statistics given by yi minus 1. What's cooking? I take the gap between y2 to y1, y3 to y2, the gap between yi minus 1, I going from 1 to n. Now you see what's happening. I get n such gaps, including the, for example, the first gap when I is a 1, this is just the gap from y1 to 0. So that's where the yi is 1, this becomes a y0, and so these are mathematicians' inventions. y0 is 0, so that this is a first gap. So this is n minus 1 points, break up this interval 0, 1 into n gaps, n spacings. That's the reason I picked n minus 1 points. N minus 1 things break up the interval 0, 1 into n pieces. This, there is in fact, intricate mathematics, and in some places they call these are called the pieces of a broken stick. You cut at n minus 1 places, then it breaks up into n pieces. That's what these gaps are. These gaps are the n pieces, or Ti. Under the null hypothesis, the observations are uniform from 0, 1, and the corresponding spacings I'm calling TIs. Ti is a gaps between made by the uniform observations. And I might also use the notation Di for a more general spacings later on. Okay, a more explicit notation, we shall have to use a subscript n also. I'll explain briefly. So these order statistics, they depend on how many observations you're ordering. If you throw one more observation, the 10th largest value may become the 11th largest. So what you call order statistic of order 1 will depend on not only the order statistic of order I, but also on the sample size that you deal with. So the order statistic should be more formally written as I and n. T also should be written I and n, but I say more explicit notation. But okay, writing T1, T2, Tn as a vector T, the joint distribution of T vector can be shown to be n minus 1 factorial, where Ti's are non-negative and Ti's add up to 1. Ti's are these different pieces of the broken interval 0, 1. So they add up to 1, total of the length, total length of all the gaps. And the Ti's are non-negative. They are the ordered difference of the ordered values. And one takes a bit of work to show that the joint distribution of the order statistics is n minus 1 factorial. Now, as I told you, it's going to be a sort of mathematically oriented talk compared to the other one, which is very nice. You get both flavors in one day. Okay, so this is, so these kind of random variables are called exchangeable random variables. They are not independent, but exchangeable. Exchangeable means T1 behaves the same as T2, T2 behaves the same as T3. They all have the same characteristics, same marginal distributions, and so on. So and they are not independent because summation of Ti is a 1. They cannot be independent because if T1 is large, T2 has to be small because the sum of them is 1. So they are not independent. And Ti's follow a beta distribution. This I said, this they called a Dirichlet distribution. A Dirichlet distribution is an extension of a generalization of what we all usually learn called the beta distribution. A Dirichlet distribution, and that is the joint density of a Dirichlet of this particular type. Okay, now I'm giving you some results here quickly. Ti's follow a beta distribution. Ti by itself is a beta with 1 and minus 1. And Ti comma Tj, any pair of them is a Dirichlet with 1, 1, and minus 2. And one can verify expected value of Ti is 1 over n. And the covariance of Ti comma Tj is given by minus of this. And if I is not equal to j, if you pick any two gaps, I and j, I are not equal to j, then you can see that the covariance is negative. Just like as I was explaining, if Ti is large, Tj has to be small because they add up to 1. These are gaps of the same broken stick, right? So this negative covariance is what happens. And this is the variance if I is equal to j. And in the limit as n goes to infinity, Ti goes to 0 in probability, and n times Ti goes to a random variable, which is exponential 1 random variable. These are all little facts that can be proved in a longer course, but I want to mention them to you. So the exponential random variables have a close connection with these uniform gaps that I just described, Ti's. And one can easily check that the Ti's, I going from 1 to n, these n gaps are distributed the same as a Wi over summation of Wi, where Wi's are IID exponential theta random variables. What is this Wi's? Independent, identically distributed exponential random variables. And what is that I'm telling you here? If you look at the ratio of exponential to the sum of the exponentials, what do these guys add up to? They add up to 1, same as these guys add up to 1. But the interesting part is these uniform gaps have the same joint distribution. That's what that notation is. These guys have the same distribution as this set of I going from 1 to n of these things. And for simplicity, we can take theta to be 1. And this is equivalent to saying Ti's are distributed as Wi's are the exponential random variables, given the summation of Wi is a 1. So that's another way to write this. If summation of Wi is conditioned to be a 1, then the summation of Wi, of course, adds up to 1. So this is another way of saying that, is to say these gaps behave like Wi's, given that the summation of Wi is a 1. So these are actually related to the interarrival times of a homogeneous Poisson process. Interarrival times. In a Poisson process, homogeneous Poisson process, interarrival times are exponential. So these gaps are like exponential random variables conditioned on the total being 1. So there are a lot of interesting connections in the gaps of this kind. So one can use variety of tests based on the spacings, and the general form of many of these tests, which are symmetric in spacings, is of this form. I'm going to tell you that you can construct a lot of tests based on the spacings, DI or TI as we call them. It's functions of this form for testing goodness of fit. I'll elaborate on this in the next slide, where H is a function, a general function. I'm suggesting to you, for various functions H, you get various statistics. For doing what? For testing goodness of fit. That I originally wanted to tell you about. And there is a nice paper by Ron Pike, 1965. It's a very sort of dated paper, but it's a good review paper, Pike, 1965. And this is the kind of statistics that I'm going to tell you about. These are tests for using spacings for goodness of fit. What kind of tests? You might wonder, what is that H function? If H of x is, say, minus log x, or Hx is x log x, you get statistics of this particular form. Okay, so various statistics of this nature have been suggested in the literature, dozens and dozens of papers. And I suggested a statistic based on h of x, which is absolute x minus 1. What does this result in? If h of x is x, absolute x minus 1, I'm talking about a statistic NDI minus 1. What is that I'm doing? This is same as pull the n out, is di minus 1 over n. This makes a lot of sense now. It should make a lot of sense because you remember these gaps, their expected values are 1 over n each. And so di minus 1 over n. The gap, how large is the gap? What is the expected length under uniformity? They are supposed to be 1 over n each. So how far apart are these gaps from 1 over n? Certainly not all the gaps will be 1 over n, unless the points are equidistantly placed. So this is a very interesting statistic. Look at the difference between the DIs minus 1 over n. And this has been called Rao's spacing statistic when I was still known as a Rao. I was known as J.S. Rao for a long time. So I can't change the name of the statistic any longer, but nevertheless, this is called this statistic I suggested in connection with testing uniformity on a circle. And this is very commonly used for testing uniformity. What do? You have points on the interval 0, 1. Look at how far apart one point is to the next point, the di's, and subtract the expected length. And look at the difference, absolute difference between these two. Some of the di's may be bigger than 1 over n, some may be smaller than 1 over n. I'm looking at the absolute difference sum. Okay, now h of x may be x to the alpha. And then this leads to a statistic of this form, n di to the alpha. And now, you know what? Exact and asymptotic distributions, there are many, many approaches. So people have been working on statistics of this nature for testing uniformity, for testing goodness of fit. Goodness of fit we translate to uniformity. And those kind of tests, people have used various methods based on conditional approaches, based on characteristic functions. I use the word many, too many times because to say there are several approaches to try to get asymptotic distributions, exact distributions of these statistics. So it's a whole literature on this topic. Rao and Sethuraman was a faculty member at one time at ISA Calcutta temporarily. Later on, he moved to the Florida State University. He and I wrote a paper where we said this kind of statistics, the kind of statistics, the S and H of NDI, one can work on them in a very unified fashion. And what did we suggest? We said, pick what we call an empirical distribution function of the normalized spacings. What is normalized spacings? If you multiply with n with di, I call it normalized spacings. You remember I told you di's disappeared. Gaps go to shrink as n becomes large. Di's go to 0 in probability. But if you multiply by n times di's behave well. They become exponential. So n di's are called normalized spacings. So we look at the empirical distribution of the normalized spacings, which is how many of the NDIs are smaller than a given x for some x in 0 to infinity. This is an empirical process. And we look at the whole empirical process for different values of x. And then say this statistic Sn that I was interested in can be written as the integral of this kind and can be thought of as a functional of this empirical process Hn of x. And then we use the invariance principle to say any such statistic for functions h, different functions h, you can tackle them. You can get distribution theory for statistics of this nature. Now, I don't want you to necessarily mull over each of these in great detail, just get a gist of this because I'm going to give you a big overview of the big picture of the spacing topic, gaps between points. And one of the, and in fact, you know what, I'm going to mention soon, we are planning to write a book. We have started writing a book on this topic of spacings. We're up to 250 pages so far. And so it's that a wide topic I'm trying to talk to you about. Okay, so one of the typical theorems of this paper says, if you take uniform spacings Tk minus a exponential random variable W, then this is a normal distribution with this variance. What is this variance? Give me your H. I can get you the variance. I can get you the mean is this guy. So given any H, I can tell you the exact asymptotic distribution of the statistic of this nature. So there's a general theorem of this kind under some regularity conditions. So this is instead of trying to struggle with each statistic separately, we say one can do this. Okay, now there is a large literature on testing. Now you might be all wondering, what is a good H? You keep saying H can be this, H can be that. So And then there are all kinds of efficiencies. This is a non-parametric concept, testing uniformity versus non-uniformity. And there are concepts called Pitman efficiency and Bahadur efficiency. And Bahadur, incidentally, I told you, was on my PhD committee, and he says to me, after looking at my thesis, I used Bahadur efficiencies in there. He says, Bahadur himself says to me, oh, you know, Bahadur efficiencies are not all that trustworthy for small samples. They're only large sample concept. I told him, yes, I know that. And I use some simulation results for small samples. And so that's interesting. Bahadur efficiency is one concept of comparing efficiencies of various tests. Okay, very briefly, the statistic corresponding to h of x is x squared has the largest Pitman efficiency among all symmetric tests, while the test corresponding to hx is log x has the largest Bahadur efficiency. A recent paper by Murakumoto and Jammalamadaka on asymptotic first order and higher order efficiencies, and forthcoming comprehensive monograph being planned on the topic of spacings. I just mentioned about this book. I keep changing the year. Oh, it's supposed to come out this year, but I doubt it. So this is a book on spacings that we are writing. So it's a huge topic, and I'm trying to give you a gist of. So I'm done with the first aspect of my spacings talk, which is, I don't know if I'm going to be done in time, but I'll take extra 15 minutes, hopefully, because I started a bit late. And this is estimation. Now it's jump to a new topic, estimation problem. Estimation is maximum likelihood estimate. We all know that. I won't get into this in great labor this point. L theta is the product of all the density functions, f theta xi's, I going from 1 to n. We maximize this with respect to theta. That's called the maximum likelihood method. And it's liberally used. It's very nice. It's ease of formulation, calculation, interpretation, nice properties, and so on, under some regularity conditions. But then it turns out it has its own blemishes. The maximum likelihood method need not always exist. Likelihood may become unbounded, as in the simple case of normal mixtures. So it turns out if you take a mixture of two normal distributions and try to use the EM algorithm, I'm going to give you an example later on. And so in normal mixtures, maximum likelihood estimate don't work. The procedure doesn't work sometimes when you don't have densities. For example, I work with what are called stable distributions. Stable families don't have easily writable densities. So there's no way to write down. And the MLEs may fail to be consistent even when it exists. For example, Niemann-Scott example and others. Some of you who teach statistics courses might be giving such examples in your courses once you discuss ML methods, maximum likelihood methods. Bahadur has a nice paper again on the inconsistencies of MLEs. So what do I suggest? I suggest a method based on spacings for estimating parameters. We are done with testing goodness of fit, uniformity tests. And now I'm going to tell you how to estimate the parameters, unknown parameters, maybe one, maybe two, any vector of parameters. So what is that I'm going to do? You give me a data x1, x2, xn minus 1, let's say. And then transform the ordered observations to 0, 1 like this. Pick f theta x0, f theta x1, f theta xn minus 1. And again, I'm putting this x0 was not there in my original data. That is my 0. And this is my 1. Now you might wonder, where is f theta? F theta for a given model, for a normal distribution, if I take parameters to be mu and a sigma square, given mu and given sigma square, then I have a mu and sigma square. That is the theta I would use. I'll tell you how to find this theta in a minute. So then I find the di theta, which is the spacing, f theta xi minus f theta xi minus 1. And these are uniform spacings if theta is the true value. If theta is the true parameter value, this is the true distribution, and that makes it a uniform distribution, uniform order statistic. So this is a difference of uniform order statistics. So these are uniform spacings if theta is the true value. So this is my principle of estimation. Find that theta which brings the observed spacings, these di thetas, close to 1 over n. Why? Uniform spacings are supposed to be close to 1 over n. So that's what I'm going to try to do. Suppose you think of these two models, F1 consisting of D1, D2, Dn. What are these? These are the observed spacings with theta as the parameter sitting there. And F2 is the 1 over n that is supposed to be the expected values of these di thetas if theta are the true values. So I want to find that theta. Di's are the observed values, 1 over n their expected values, one theta hat that brings them close together. What is the theta hat that brings this F1 vector close to the F2 vector? You might even think of this as some kind of a probability vector adding up to 1. This is also a probability vector. So I look for divergence measure between probability distributions, and these are sort of in the genre of distance-based methods. There is something called scissor divergence measure between two CDFs. These are things you can take back with you and learn to use someplace else, not necessarily in this context. So this is a guy, Scissor, I'll give you a reference at the end, 1963. He says for any two distributions, F1 and F2, any two CDFs, you can define as divergence measure, H, IH. For example, if H is log, this becomes a Kullback-Leibler distance. So this is a more general measure. So H is a convex function and so on. So this is a non-negative quantity IH and is 0 if F1 is equal to F2, is a semi-metric, and it doesn't have one of the properties of metric. For any convex function, T theta, if I now go back to my F1 and F2 and apply this divergence measure for this F1 and this F2, although this look intimidating here, F2 is after all a 1 over n is a discrete distribution. So this integral is nothing but a summation. So it becomes this. So this is my procedure. Find me a theta which minimizes for some h, this quantity theta. The resulting minimizer theta hat is called the generalized spacings estimator, GSE of theta. What is a generalized spacings estimator? Something that minimizes this quantity, h of NDI theta. H is again something under my hands. We can control it. We'll talk about it. So for example, I'll give you a simple example. If you take a n-1 observation from a uniform distribution, this is the uniform distribution, a rectangular distribution, where theta is in the real line. MLE is any theta hat in the interval. It's not unique. Maximum likelihood estimate is not unique. But if I use this hx to be this or this or this, I get theta hat to be x1 plus xn minus 1 over 2, the smallest one and the largest one over 2, which is the UMVUE. So you see what happens? My spacings estimator beats the MLEs. MLE says, so it throws up its hands and says it can be any value in between these two numbers. But my estimator gives you a precise number, and it is the uniformly minimum variance unbiased estimator. Okay, given the time constraints, I'm going to pass on. This is another example. This is a practical example of this kind. This data goes back to Darwin, apparently. These two guys, Aitken and Wilson, in technometrics, they looked at this data on self-fertilized and cross-fertilized plants and the height of plants, and they were trying to, they think it's a mixture of two distributions because self-fertilized plants and cross-fertilized plants. So they were using the EM algorithm, expectation maximization algorithm, and they get normal mixtures of mu1, mu2, sigma 1, sigma 2, and the mixing parameter P. And they get, I'll just show you the results. they get this to be mu1 hat, that to be the mu2 hat, this sigma 1 hat that goes to mu1 hat, sigma 2 hat that goes with the mu2 hat. And you see the variance of sigma 2 hat, 430. And you take my spacing space estimator using hx is minus log x or x square or any of these. I get sigma squares to be very tidy. Mean is the same, but variance is 3.28. And the variance in some 90 is 24.8. So EM algorithm gives huge variances as opposed to variance estimates which are smaller and realistic. So that is what I mentioned a while ago. In connection with mixture of two normals, ML estimation is no good. EM algorithm uses maximum likelihood estimation. So I'm trying to prove the point that this spacing-based estimation is. Did someone have a question? Okay. Okay. Now, here is a result theorem. Under some mild conditions, one can show that this kind of spacing-based estimator, Ghosh is one of my students. He is a professor at the University of Nevada, Las Vegas. And he and I wrote a paper and in which we show asymptotic normality of the spacing-based estimators. And what do we show? If theta naught is the true parameter value, this spacing-based estimator converges to minus theta hat converges to a normal distribution with this variance sigma square h, whatever h you use. And what is this sigma square h? Oh, big long expression here, but that's the expression. So one might ask, what is a good h again in this case? And I think I'm telling you, scratching the surface, so I'll tell you, hx is minus log x, and one can check sigma square h is a 1 in this case. If you take hx to be log x and calculate all these things, in this variance, you get sigma square h to be 1 is 1 over I theta naught. And that should remind you this is the MLE, maximum likelihood estimates have this. So that asymptotically, if you take hx as minus log x, they are as efficient as the MLEs. Okay. Now, this MLEs have been, this has been called the maximum product of spacings method and was discussed by people in 1983 and 84. They proposed this as an ad hoc method, and our result shows we can talk about, they just picked one particular h and worked with it, and they call it a maximum product of spacings estimator. Because if you take hx to be minus log x, it works out to be this guy here. If hx is minus log x, this becomes the product of spacings. So they try to maximize the product. I was minimizing this h. If we put a minus sign also, it becomes, so they call it a maximum product of spacings estimator, and they wrote papers on this. But we say, we proved their method gives you one of the spacings-based estimators and is perhaps a better one than the other class of estimators. Okay, now, I'm going to move on to what I call two sample problems. Two sample problems and rank tests. What does one do if you have two samples that we wish to compare? I covered testing of hypothesis, goodness of fit, estimation of unknown parameters using spacings. Now I'm going to tell you how to use spacings for comparing two samples. So x1, x2, xm minus 1 be IID from some distribution f, y1, y2, yn be a second sample, independent sample from nth CD of G. Very typical problems. Two samples. How do we compare two samples? Whether f is equal to G. The classical problem is to test the null hypothesis that these two parent populations are identical. F is equal to G. So this is what we do. If you have normal distributions, you use a two-sample t-test or something, right, for them comparing means. So these are non-parametric context, I'm going to tell you how we might use spacings. So what I'm going to do is to order these x1, x2, xm minus 1. Let x1, x2 with parentheses be the ordered x observations. And let sk be the number of y observations that fall inside the kth gap of x. That is, look at the gap x1 to x2. How many y values fall in between? Y is the second sample. So what is sk? Is the number of second sample observations y that fall inside the kth gap made by x. xk minus 1 to xk, for k going from 1 to m. These are called spacing frequencies. Frequencies of y that fall inside the spacings made by the x. And these have something to do with the rank tests and like Wilcoxon and Mann-Whitney, and there's a famous book by Hack and Sidak, Theory of Rank Tests. And what we do, myself, when I was still known as a Rao and Holtz in Sankhya way back, we discuss comprehensive theory for tests of the form summation of hk, sk, k going from 1 to m. What kind of distributions can one get by picking up functions hk of sk? What are sk? Sk are these counts, spacing frequencies. Okay, and a typical result of this kind, and the simplest one of this kind, which is symmetric in k. You see, this h of k can vary. If h's are all the same, I give you a result going back to this paper. H of sk minus h of eta is normal sigma square h. This is a theorem. What is this eta now? This is not the exponential random variable anymore. This is geometric random variable with probability mass function given by this. So in other words, I'm into trying to prove very general results, if possible, and then say what can let people put h to be log x, h to be x square, whatever they want to do. Okay, so this is for this still already a specialization, h of sk where h's are the same. So this is a typical result of this kind. One can derive locally most powerful tests and against close alternatives for various alternatives. And we show that tests based on this SKs, spacing frequencies, are comparable to rank tests. One for one, they match. And what is more, the major advantage of such tests based on SK is that they are useful in comparing two circular samples. Now, some of you may be expecting I will somehow tie it up with circular data, and you are not going to be disappointed, because if you have samples and circle, two different samples, there are no ranks. You can't rank data on a circle. There's no zero. Where do you rank from? On the other hand, you can take these spacing frequencies. You take first sample, take the gaps made by the first sample, and observations of the second sample that fall in between the gaps. There are no ranks, but there are spacing frequencies. So that is where my motivation came from. There are no ranks. So these tests that we are inventing based on SK are useful for circular samples also. And the M-step spacings, you know what? This is a talk I was going to give this afternoon, this evening, on my computer for University of Kerala, about the fact that the M-step spacings is when you go from not I plus 1 to I, but I plus m to I. That's called a DIM. That's called a M-step spacings, where m is bigger than 1. What's cooking? I jump from the first observation to the third observation, second observation to the fifth observation. So jump 3 steps, 2 steps at a time, 3 steps at a time. M steps at a time. They're called M step gaps. And so there are some connections to, in fact, the point is that this is going to be comparable to chi-square tests. And we show that these spacings-based tests are better than the chi-square tests. So I'll only read this part here, the last paragraph here. Spacings methods have been shown to be more efficient than chi-square methods in the context of testing. And so that's what, so there are a lot of further extensions possible. And so I'm going to pose some research questions here. I'm going to take 5 more minutes and wrap it up. Okay. Extensions to multivariate data. What does spacings, how do they go into multivariate data? What does that mean? Multivariate data meaning what? You have data on the plane, let's say, bivariate data on height and weight. What are spacings mean? Spacings, I said, are ordered values between X, one single sample. But if you have bivariate sample, how do you order? There's no order statistics there are some concepts, but there is no ordering business. So for spacings-based goodness of fit in multivariate case, one may use nearest neighbor distances. So what we do is we pick a point in the plane, let's say 2-dimensional data. Pick a point on the plane and pick the nearest point to that point in 2 dimensions. And then make a ball around it, nearest neighbor ball with that radius. Those are called nearest neighbor balls. And look at the probability of that ball. So there are ways around it. As one of my other students, Zhao, he is a professor in Australia. I forget the name of the university now. But anyway, so for multivariate data, one can do goodness of fit tests. And Bickel has done some papers on this also. And then for spacings-based estimation in multivariate distributions, I have a paper also on this topic. This is spacings-based estimation in multivariate case. So I know some of you will have questions about what about multivariate? Are there spacings? Spacings, well, there are concepts, but not the time. Okay, higher order spacings. Higher order Edgeworth type expansion, higher order asymptotic expansions. You know, this is a typical question. You know, when you teach basic statistics course and say normal approximation to the binomial, students immediately ask you, how large a sample should binomial be before I use a normal approximation? Right? That's a typical question. Normal approximation kicks in when n is large, n goes to infinity, right? That's what asymptotic distributions are. Central limit theorem is. So then people have done what are called higher order asymptotic expansions, like Edgeworth type expansions for spacing statistics. So what is that about? Not just the first order saying is a normal distribution that I gave a result of this kind some time ago. And this is a kind of typical theorem of this kind. The SN, the statistics based on spacings, minus the expected value divided by some variance of the sigma that came there. We stopped by saying that this is a phi of x, the CDF of a normal distribution. That is the central limit theorem. That's the kind of asymptotic normality. But then you can also write down a root n term, second order term, in the distribution of this CDF for this spacing statistic, not only phi of x plus this term, plus another term. Those are called higher order expansions. This term will have 1 over root n, and that term will have 1 over n, so that you will have more and more precise approximations for the normality, additional correction terms, so to say. So there is any number of such things, and so I think I'll stop there, and I'll give you some references. Aitken and Wilson, mixture models, outliers, Bahadur. Here's the examples of inconsistency of MLEs, and Cesar is the guy who suggested that metric, semi-metric, and this is the families of two sample non-parametric statistics, and higher order expansions, efficiency of tests based on spacings. And this is a very old paper, but it's a good discussion paper also, going back to Ron Pike. And oh boy, I have put a lot of references here. And this is the Sithraman paper on the Annals of Statistics. And this is a recent paper on the class of asymptotically efficient estimators based on sample spacings. Okay, I'm going to stop there. Okay, I'm open for questions. Yes.
Sir, actually, there are two questions, sir, basic questions, sir.
Okay.
One is, which test is more reliable, chi-square or t-test or f-test?
Okay. Now, you see, the t-tests and f-tests are what we call for parametric models. If you tell me the samples are from a normal distribution and you want to compare whether two samples, two normal distribution, normally distributed samples, I use a two-sample t-test. Or, okay, now you can also use a f-test in that context, but f-test is only it's only good for testing two-sided alternatives, not for one-sided alternatives. But in general, these kind of tests are specifically focused on a particular parametric model. And they are not applicable if your data comes from a different distribution, or you don't even know what the distribution is. Those are called non-parametric. So all my talk today is about non-parametric statistics. No parameter models are assumed. I finally show something is asymptotically normal, but the kind of statistics I get are all based on assuming data comes from some distribution F. I don't tell you what F is. Is F a given F not? So these are non-parametrics. So when you compare, a chi-square test is good for non-parametric context. So these are competitors. Chi-square tests, empirical distribution function-based tests, spacings-based tests. And these are all good for testing this kind of general hypothesis. Non-parametric versus parametric, yeah, that's the difference.
Next question is, which test is suitable for analyzing a question with 4 options?
Okay, 4 options.
Yes, sir.
I'm not quite sure what the question is, but what might be questioned is, you might have 4 hypotheses, H1, H2, H3, H4, multiple hypotheses, then it's called a multiple decision problem. Multiple decision problems, I teach a graduate course, I just finished teaching one, and we have different procedures for those multiple decision problems. We might be able to use some kind of discriminant functions and alternate approaches to decide which of those hypotheses, Bayes methods, for example, things like that, to choose between several hypotheses. And in general, the testing of hypotheses that we typically teach is the H0 and H1, and F0 and not F0. And so if you are interested in testing multiple hypotheses, then you need to look into alternate literature on Bayes methods or multiple testing context.
Okay, sir. Now, may I request Professor P. Tirupatirao Garu, Dean,
Thank you, sir.
Ramanujan School
Namaste,
of
sir.
Mathematics.
Professor Srinivasarao garu.
Very much, very good evening. Namaste to you.
Really, it's so fortunate to me on two reasons. One is they have assigned a job to sum up your lecture. So it's a very effective time for me to listen almost every word of you. Okay. So therefore, I'm very happy. Today, I realized that a great teacher come researcher is within you, sir. And really, it is a rare phenomenon that we cannot observe both persons in one individual. That means teacher and researcher. It's my perception. It's my perception that what I observed, teachers are mostly disseminating the information which is existing. Researcher go for new discovery information. Today, you have unveiled a good researcher with his good teaching things, how we can make our research communications to even a layman also. Sir, you have started with a very humble beginning that a variable, random variable occurs at different points of time, and that generates the gap between the space you defined on the linear line, linear space, on a continuous time with the range minus infinity to plus infinity. Occurrences you have considered at random points. So therefore, the distance between the random points you have considered as gaps, and as that occurrences have some random variable, similarly, the gaps between the occurrences also random variable. So nice way of starting that. And you have synchronized these similarities, these to, it is something like occurrences, number of occurrences, as well as arrival, you can say, events of arrivals, or in between arrivals, there is called inter-arrival time, how it is follows exponential distribution, and how these spaces or gaps, you can say gaps again a random variable, which have a probability distributions, all the properties you have explained. And very interesting is in a single sample real line space, you have explained a very nice way that how this can be seen as a random variable, what is the probability distribution, and what are the various characteristics, how you estimate the parameters, how you verify the testing, etc. And further, if you propose some probability distribution to the gaps and using the non-parametric approach, goodness of it, how can be done? These are all very wonderful things you have shared, sir. And random variables, gaps of random variables. These two things are very novel to me to listen this today's topic. And later you have extended for two samples case and spaces in between spaces. So Y has some phenomena, X has some phenomena. Combining to this on a linear space, you have explained very vibrantly, sir. With all clarity, we got the content. And further, you have extended that. Assume the gaps in a circular space. Linear space you have started and expanded it into the circular space with single samples, circular space with a double sample, and finally you have end up with multi spaces on linear space as well as linear line or linear space, multiple variables on linear space, multi-variables on circular space. Of course, I think, I hope that there is slight difference between directional data analysis and samples on circular space. Am I right, sir? I hope that there is a difference between directional data analysis and the spaces on a circular space. I mean, gaps in between, gaps on a circular space. So you have proposed certain properties and theorems and this likelihood ratio tests, my MLEs, as well as LMP tests. Very, very interesting, sir. So really, I enjoyed this lecture, and it is a new experience to me. So to know a new concept this way, the gaps in between random variables is again a random variable, and how we can make it as a distribution properties. As you said, if you handle this what we call it as order statistics or a ordinal data related studies, it finally comes under categorical data, and that categories can be converted as a continuous or scaling variables also. You can propose different probability distributions, and accordingly properties can be explored. So very nice experience, sir. And the scope also you have given a very nice way, that is nearest neighbor distance, nearest neighbor ball point, spacing based on multivariables. So these are all, initially I thought that this gaps related comes under ordinal data, means that is order statistics, probability distributions may be more appropriate in this context. And however, once we are able to convert this ordinal data as a scaled data, and we can have other assumptions also. Overall, we enjoyed and the lecture. You have a begin with a simple thought of a random variable notion, end up with a very vibrant scope for the study. Really enjoyed, sir. Thank you very much, sir, for your nice talk, and I thank organizers of Geetham University for